All right. Hello, everybody, and welcome to MetalCon Live. I'm Kaylin, the Trade Show and Event Specialist for MetalCon and PSNJ. And this week we are joined by Bob Zabcik of the Metal Construction Association and Zabcik Consulting. Please ignore the typo on the screen. It is Zabcik Consulting. And he presents EPDs and LCAs. We have them, now what? An in-depth look at how these products affect our buildings. Today's presentation is brought to us by the MCA, and to learn more about the MCA and the benefits of membership, as well as how you can become a member, you can reach out to Jeff Irwin. His contact information is on the screen. Be sure to join us on February 2nd as we're joined by Carl Feldman of Hinge Marketing as he presents ways to attract and retain employees during the Great Resignation. Speaking of future education, do you have an idea for an interesting course that can be taught at MetalCon? Be sure to submit it. Our call for presentations is open now until February 18th. We want to hear what you want to talk about. We want to make sure that we have fantastic education for everyone attending this year. Lastly, before I hand the reins over to Bob, please be sure to submit your survey at the end of this course. At the end of this presentation to ensure that you receive your certificate and your credit. If you have any questions during this course, please submit them in the chat box or in the Q&A section at the bottom of the screen. Without further ado, I'm going to hand this over to Bob. Bob, take it away.
Thank you, Kaylin. Let me switch over to my screen here and make sure everybody's looking at the right one. Okay, you should be looking at my starter slide. EPAs.
Yep, we're seeing that right now.
Great. Thank you very much for the opportunity to talk today. I'm here as Kaylin said, as a representative of the Metal Construction Association. And we've been working pretty hard on a lot of our sustainability directives. And the top of that list is our environmental product declarations, which actually were completed a number of years ago. I think 7. They've even been renewed since then. And really, this is not just directed at architects, but also folks in the market and as membership. Okay, this is all well and good. We've done this work. Now what? Okay. And so I'm going to go through a couple of things. I just wanted to real quick share what our mission at MCA is. We're here to grow the use of metal in the building envelope, and our vision is to be represented as authoritative voice of the Metal Construction Association, metal construction industry, excuse me. And we're going to do that through 3 things, primarily our efforts to promote, educate, and focus on the aesthetics, performance, values of metal, bring the stakeholders and industry folks together and take that message to the building owners, architects, consultants, contractors, and authorities having jurisdiction. I also going to give you a little eye candy. This is a shot that I took personally at the Salvador Dali Museum. So we had a great architect experience at MetalCon last year in Tampa, Florida, and this was the like I mentioned, our outreach event at the Salvador Dali Museum is absolutely beautiful, gorgeous building, and just wanted to show you that. It's just we had so much fun and great chance to meet new people and network for the first time since COVID. It's just a fantastic experience, and we're looking forward to more of that. So I'm going to give you a pretty good introduction because I know LCAs and EPDs and things like this might be new to a lot of folks. We've been working with a company called Sphera on our LCA development. Our program manager is Underwriters Laboratories, so you'll see their names in there as well. I got these things from the Sphera website, but they really are good base, simple definitions. What life cycle assessment is. It's defined as a systematic analysis of the potential environmental impacts of products and services during their entire life cycle. It's really important when you're analyzing LCA to understand what the functional unit is. The functional unit is a reference unit for scaling the product system based on the functions provided. In our example, it's 100 square meters of wall panel. pretty straightforward, but when you start comparing different materials, sometimes they have different functional units, you have to remember to do those conversions, and that's not always easy. It's something we'll talk about today. And you also have to understand the idea of a system boundary, which is just a description of activities within a product life cycle phases that are included and excluded from consideration. That's really best shown by graphics. And I got one showing up, coming up in a second, show you what that is. Well, as you do LCAs and you're picturing these flows going in and across the boundaries, you'll talk about reference flows a lot, which is the amount of a resource needed to provide a functional unit to express in whatever unit is appropriate for that reference flows, mass, energy, volume, something to that respect. And then those flows kind of break down into two things: a product flow. So this is the flow of input products and output products that go through this process, and they kind of drag through these processes that you're analyzing, and they pull with them elementary flows, which are reference flows of raw materials on the input side, or byproducts on the output side that crosses the system boundary. This is all dry stuff. But here's a really good graphic that I think kind of shows that better. This is actually from the ISO standard that dictates LCA principles and frameworks, 14040. And it shows that I draw a system boundary around my process, production of a product in our case, the process I'm trying to isolate. And outside of that boundary is called the system environment. Inside is the system itself. And we can bring into inputs, the examples here are other systems, which is a product flow, or elementary flows, which are what might be resources that are used. Water might be a good option, for a good way to example of that. They throw through that boundary, and then whatever you're analyzing according to the scope of the LCA happens. You break these down as subsystems. You look at the materials and flows between those subsystems. You as the consumer probably don't need to worry so much about that. We as manufacturers and our LCA consultants certainly do. But as a consumer of an EPD or an LCA, that is, it's good information to have and understand, but not necessarily critical to your application of these things. You're looking at what comes out of the back end, the elementary flows, which are, the discharges to the system environment, and of course the product flow, the thing you're after, right? This is what you're trying to apply. And so that brings up more definitions, a formal definition of life cycle assessment and life cycle inventory. I'm going to focus in on inventory first because it's phase of the life cycle assessment involving the compilation and quantification of inputs and outputs for a product through its life cycle. Essentially, what that means is I've got a big giant database of these materials going through these flows, and the process of it going through that flow generates an impact. And so I'm building a database of those things, and I'm accessing that database as part of my LCA. And what you'll find is these databases, and they come from lots of different sources. They are also driven by ISO standards, and they are compatible, but not always in sync. And it's something else you got to be very well aware of, that you're not applying getting out of sync between your database and your processes. And then you go through a couple of really important phases of an LCA, and it's a life cycle impact assessment. That's the phase of the life cycle assessment that's aimed at understanding and evaluating the magnitude and significance of the potential environmental impacts for a product system throughout the life cycle of its product. That basically means that this is where the rubber meets the road. You're trying to define what the impacts to the environment, the world, what they are from the result of these processes and these flows. This is where, like I said, it's where the rubber meets the road. It produces the metrics that say this is what we're going to judge this product, this system by. And then life cycle interpretation, which is when you take the impact assessment and your inventory, and then you look at how it's related to the defined goal and scope of the LCA that you're going with, and that's what you're basing your conclusions and recommendations on. And that's an important part of LCA, obviously. But really what for EPDs, and we'll talk about the differences and how those are, but what EPDs really drive into is the life cycle impact assessment, the LCIA portion of that. Okay. I'm gonna skip allocation for now. We might come back to that if we get some questions, but allocating these flows is really kind of like if you've ever, allocating financial flows, and relates to how recycled products are handled. We might come back to that if there's some questions, but here's the observation that I hope you're coming away with. Number one, the LCA is a very versatile tool, very scientific, very systematic. And it can be applied in lots of different ways with different results because the goals and the scopes are different. And that works really great with a whole building approach. When I'm sitting down, I'm trying to come up with the best, most sustainable answer in a building. I know what that building is there for. I know what how it's going to be used. I know its expected life cycle. I have all that information. And so that's what makes this really work well with a whole building approach. But now as manufacturers and consumers of this data, we're all working with different buildings. We all have different things that we're trying to accomplish. So how can I take these results and apply them across different projects in a systematic way? It's a really difficult question. It's what EPDs and PCRs really try to drive to. And they do that at a high level through standardizing the scopes, the impact categories, et cetera, and using consistent data and modeling practices. So the modeling practices are consistent with the data, but the modeling practices are also consistent with the standardized scopes and impact categories. And that is really important, obviously, if you're going to be able to want to compare results between alternatives. But there's other things you need to be cognizant of. First off, ISO standards that drive this whole thing require peer review if you're going to be using the results to compare between competing alternatives. And that's a very important aspect of this because obviously you want some neutrality and some transparency in that process, but you also want it to be correct. And you want to make sure that you can put this together as consumer of this data. You're getting all this data from different sources. You need to be able to, with confidence, to put it together in a way that gives you a meaningful answer. And peer review is part of that. But really, to me anyway, the most important part, and sometimes the more difficult, is addressing inconsistent functional units. And here's an example. If I'm looking at metal cladding versus concrete tilt wall, my LCA and metal cladding might be 100 square meters. My tilt wall might be in cubic feet or cubic yards of concrete. How do I go from one to the other? If I've got a given building, I'll know what that is. I'll look on a set of plans. So here's my wall thickness, and I figured it out. But in a standardized approach where I could have any wall thickness, what do I do? And you have to address those inconsistent functional units as a consumer of that data. And that's what really a Type III environmental product declaration attempts to do. It is governed by another ISO standard, 14025. Sorry, I've got that one messed up. It requires some consistent approaches in terms of flows and how you're addressing recycled contents and closed loop versus open loop approaches, et cetera. And it does that through the use of product category rules, or PCRs. So a PCR is another document, a third document that standardizes the scopes, impacts, et cetera. This is at a very high level. It does a lot of stuff besides just this, but this is what's relevant to our discussion. And it also requires that key assumptions that you're making in this analysis be documented so somebody can understand it, read it, know that what they're looking at. And as part of that, it cites relevant standards, and that will help the user and resolve those functional unit disparities and then turn around and aid in comparisons. So this is kind of a graph I put together to try to show how information flows back and forth and why industry involvement is really important. As members of the Metal Construction Association or other trade associations who've undertaken these efforts, the members are really the source of three things that these documents or these processes that produce these documents have to consume. First one is expertise. We all know a lot about use of metal, but not necessarily how it's made, how those things, how metal cladding is made and how it affects its use is something that really is going to come from a manufacturer. Case in point, standard details or suggested details, recommendations on fasteners, those kinds of things. That expertise of those of the manufacturing side of this has to go into those product category rules. We also supply specification data that is then consumed by the Type III EPDs, because without having specifications, you can't know that you're comparing two products that are indeed equal to each other in terms of what they deliver. And of course, the most important thing, at least the most obvious thing, is we're producing the data. We manufacture these products, and we know the amount of power, the amount of water, the amount of input materials we use. And that all has to be, that process right there is really long. That's what took us the longest time in developing this, gathering this on the manufacturer. And then on the manufacturing side, and we're all going to gather it in different ways because we're humans. So we have to go through a process with our LCA consultant to make sure that that data is collected in a consistent way and is comparable between manufacturers. So that's consumed by the life cycle assessment itself, which is done under a set of product category rules, and it produces this Type III EPD. I've got this green line drawn around this to show, all of this is controlled or specified by the program operator, which in our case is Underwriter Laboratories, UL. So our LCA consultant Sphera, our program operator is UL, and we produce these documents in conformance with these standards. And that's a lot of what the consultant and the program operator are doing. They're making sure that we're doing things in accordance with the standards and that what we're producing is a document that's useful. These are just screenshots of the PCRs. What you'll see is there's a part A and a part B. A part A takes the calculation rules and report requirements and documents them. That's primarily something that an LCA consulting firm would be most interested in. It goes into great detail in those areas. And then there's specific things related to the products themselves that are in part B. In the case of the MCA PCR, we're covering actually 3 different product lines: insulated metal panels, metal composite panels, or MCM, metal composite materials, and metal cladding. And by metal, I mean both aluminum and steel for roll form cladding for the roof and walls panels. So there's a lot there, but that part B, and both of these documents are available from UL, from the UL website, and they're freely downloadable. But that part B is really probably what you'd be most interested in as a consumer of the LCA or EPD data. So these, as I mentioned earlier, one of the things the PCR does is it very explicitly names your impact categories. So we've gone through this whole process with LCA. We're producing these environmental impacts, and now we have to, number one, we have to say what they are and what they mean, and then show what our equivalent unit of comparison is. This is pretty consistent throughout all building products, but you're looking at global warming potential. It's also called GWP 100, which is kilograms of carbon dioxide equivalents. Ozone depletion potential, or ODP, which is done in kilograms of CFC 11 equivalents. Acidification potential, so this is production of acid rain, is done in kilograms of sulfur dioxide equivalents, which of course combine with water and cause acid. There are all other types of acids, but these are equivalents, right? So they're done essentially in pH to compare, and there's scaling factors that happen so that these units are done in a consistent way, even though that means sulfur may not be the particular identified element in that case is been converted. Same thing with eutrophication. Eutrophication, if you don't know, is essentially the migration of nitrates from the technosphere, from humans into water streams, and then wind up in natural water deposits and cause algae blooms and fish death and things of that nature. Smog formation potential. done in kilograms of ozone equivalents, and abiotic resource depletion potential of non-renewable fossil energy resources. So, you know, the fossil fuel, as many other fuels are, they're limited. They're being produced by the earth at a given rate. We're consuming them much faster than they're produced. And so at some point we'll deplete those resources. And that's what this is designed to capture. And that's generally done in megajoules. So these are not the relevant PCRs, it's the EPDs for the MCA member products. These are hosted on the MCA website as well as UL website. So we have 3 independent documents, roll form cladding on the left, which covers again, steel and aluminum wall and roof claddings. Metal composite materials, or MCM, uses aluminum skins and some type of plastic core, and insulated metal panels, which uses steel skins with a polyisocyanurate or polyurethane-based foam plastic core. So those are 3 different product lines, obviously quite a bit different in terms of their application, certainly in terms of what they look like and how you use them on a building, which of course, and obviously different in manufacturing, which means that the data collections are unique to each one. That's why we broke them up that way. So if you open up this environmental product declaration, you will find amongst many things, a lot of other information, what the scope of that is. And you'll hear terms talk in this context a lot, called cradle to grave, or cradle to gate, or cradle to gate, or gate to cradle, gate to grave. That is something that just basically defines where is the beginning of that system boundary, where is the end of that system boundary. And this is where, if you're going to be combining these numbers or going through some type of analysis or optimization procedure that your green building program or whatever requires you to do, you have to understand these scopes. So this is why this is here. As you can see that all these EPDs that are produced by MBA or MCA are cradle to gate. So really it's focused in, and if you see what's there at the bottom row, the X's indicate the declared module. In other words, those are the processes that are captured in the NCA, and MND module not declared means they are not. So if I'm doing a whole building LCA, this will only take me up to the point that the material is sitting there at the gate of the manufacturer being ready to be picked up. And that is important to understand, because you've got to make sure that you pick it up. And of course, your installation, your use state, maybe your use stage isn't too different from material to material. Certainly your installation is going to be different from material to material. And of course, your end of life is going to be different from material to material. So it's really important, again, to understand these scopes. The scopes are pretty much identical between the 3 documents, but the processes are quite different inside of the system boundaries. So I just got a couple of graphics that I've pulled from the LCAs themselves. I'm not going to go through these ad nauseum, but I did want to point out that there's a cradle to gate coated metal coils coming in. So this is the MCA EPD is a cradle to gate EPD. However, the LCA that was performed is a gate to gate LCA. And the reason why that is that you'll see some graphic representations of this earlier, but our impacts are really driven by what our products being pulled in are. And that's up at the top where it says cradle to gate coated metal coils. So we're covering the cradle portion of it through this coated metal coil that we're receiving from a coil manufacturer or steel manufacturer via a coil coater. And as that material sits there in our plants, we've already been assigned or inherited certain impacts associated with that. Okay, so that's built into those EPDs if you have them, and certainly the LCIs that were done, it's built into those, and that's part of these databases that the software that the LCA consultant has. It's built into their software. So it just kind of comes out at the back end that it's representative of the entire process. So I just wanted to clear that up. Even though this is a gate-to-gate process system boundary, this is a cradle-to-gate EPD. So what comes out of it? Well, on the right-hand side, you've seen roll form metal cladding. That's the product you're using. And metal scrap, there's outbound transportation and recycling. Now, there's a system boundary, and then there's this inner metal roll forming process block that you see there. And I want to just point out a couple of things. First off, the waste and emissions at the bottom, they're within the system boundary, meaning they're considered in the cradle to gate EPD, but they are those elementary flows that are outbound or outputs, and they are waste and emissions. They have environmental impacts associated with them, and they are considered in this EPD. Examples are emissions, air, water and soil, solid waste treatment, including transportation. So that is wrapped up into that. That is an elementary flow that comes out of metal roll forming process. And then likewise, we have some input materials on the far left-hand side. Now, again, we've already taken care of the material that's coming in as a coated metal coil. So this is the input materials are actually consumed during the metal roll forming process. So this is things like pretreatment, chemicals, shipping, packaging materials, things of that nature, not the metal itself. And then, of course, the input energy supply, which is just the power that we're using as we manufacture these things. Now, most of those impacts related to manufacturing are driven by the input energy supply, which of course makes us regionally dependent, depends on my grid efficiencies. And so this is where things can get quite varied. But what I'm going to show you is the whole thing, the impacts are really being driven by these coated metal coils, or most of the impact. In fact, you can see that on this next slide. So this is the results, the impact results for steel roll form cladding, again, GWP, global warming potential. And I'm going to go across, there's your unit, kg, across on a row, kilograms CO2 equivalents. There's your total. And then A1, A2, and A3 are then basically your three phases that we showed you on the scope. And what you will see here, and pardon the scientific notation, but this is important to maintain your appropriate amount of significant digits. But A1 is what you're getting as part of those input materials of roll form coil. A2 is what you're contributing as a manufacturer, and is where the transport and outbounds are. Again, they relate back to that chart that I showed you. What you care about is the total, okay, which is that middle. But if you take and you look at what the round materials, here we go down to the bottom, raw materials, inbound transport, manufacturing. So if you look at what's happening here is that these impacts, pretty much all of them, are being driven by your raw materials. Well over 90% for every one of these. What does that mean? That means that the inbound transport and the manufacturing process, in this case, really aren't contributing much to the impacts. And that's important because we take heat a lot of times from the market. You're producing an industry average at EPD or LCA, and that's not as useful as product specific. Well, we're all pulling from the same coil set. So having a product specific EPD isn't going to really help you much in terms of accuracy, right? You really got to focus in on what your impacts are of the coil coming in. The next slide is the same exact thing for roll form aluminum cladding, and you're seeing the graph down at the bottom. Again, well over 90% of those impacts are experienced or log against the process. It might be a better way to put it. When that coil is sitting there on our docks, ready, we haven't touched it yet. We haven't broken the packaging. We hadn't done anything. It's there. So look at that. Insulated metal panels, very similar process, and the flows are the same in terms of what's being tracked, but the quantities that come out are quite a bit different. At least for global warming potential, you can see this is the one area where the manufacturing process is actually a significant part of the global warming potential contribution. And insulated metal panels, as I mentioned earlier, have foam plastic, and those foam plastics have blowing agents, and we're working as an industry very hard to migrate to blowing agents that produce less global warming potential. So you will definitely be seeing this driven down. This part of the reason why EPDs have this life of 5 years is knowing these kind of things happen. But again, most of the impacts experienced outside of global warming potential are all done into the inbound raw materials. And metal composite materials, much the same thing as the cladding, as you see, pretty much with the exception of a couple of things, eutrophication and the OCP is driven a little bit more by manufacturing, but still well over 80% of those impacts are experienced prior to the consumption of that material. All right, a lot of stuff there. Let's just pull back and let's talk about this from a higher level. Most impacts are experienced, as upstream, as I brought up, and that really kind of shows that industry average EPDs are appropriate, and you're not going to get a lot of accuracy increase by having a product specific EPD, and at least for these types of products. It's also important to understand the relationship between mass and area for cladding systems, not so much between those cladding systems, but back to that example I gave earlier from comparing metal cladding to other materials. Are they using the same functional units? Because my aluminum generally is going to be thicker than steel for the same product, or not same product, same profile, and that's not necessarily the case for other things I might be comparing against. And what you'll find is that it's almost like you have to design the building twice, once for one alternative and once for option A and once for option B, and then compare those results. And that's a lot of work, obviously. And that's what a lot of these tools aim to do that are out there. But these tools get a little black box-ish. You get a lot of input, a lot of stuff that you go in there and you put into this and you get this answer and it's out, and you're not really getting views of the data that's happening, what's happening underneath the hood, so to speak, so that you can know it's appropriate for your particular project. And that's really, really important to understand and peel the onion on these things. If you're really going to do a product comparison or optimization, it's not just consuming that data and looking at the numbers. You really got to understand the different design processes, different application processes. And database and software versions, what we're seeing is very important. Different pieces of software do modeling a little differently. They're all driven by the same ISO standards, but they don't come up with the same exact answer. And databases are constant states of flux, right? There's companies, groups doing new LCIs and adding these databases at all times. And so are you using the most up-to-date and appropriate database version? Another thing to remember is that these impacts are spread over time. We talk about that, but that's actually not talked about much because the EPDs anyway, because they are not really looking at the use phase. But when I take these impacts as a consumer of that data, I am looking at the use phase. I should be looking at the use phase. And so I have to take these impacts and look at them over a period of time. And it's quite simple. The longer the time, the less the impact, just by dilution. The impact itself doesn't change, but the amount of time I'm experiencing it does. And so I achieve that dilution of a negative impact. We've done a lot of work on this outside of what we've done with EPDs and LCAs, just part of general service life studies that we do. We have a service life study on metal roofing that's available for download from the MCA website. And quite conservatively, we pegged it at 60 years. A lot of the buildings that we looked at probably could have gone twice that, but we felt like that's not a useful answer. So we just kind of took a reality check. And again, most people are looking at 60 to 75 years for a building life cycle to begin with. And so what it comes down to is most of the time, you're not going to have to replace the metal roof. So if I'm not having to replace the roof, or the walls, maybe I'm just getting get away with repaint on the walls, I'm not experiencing those full impacts. And none of this is incorporated in the EPD. That's why it's important to understand that that's part of the whole building LCA that should be done. And when you part of your, if you want to make sure this is done right, you need to make sure that those impact life or those service lives are appropriate. And so you'll see 40 years cited often for metal roofs. And yeah, we have a lot of evidence that that's overly conservative. So those impacts, again, they should be considered in that proper context. Okay, and this is just one of the graphics. The service life study just kind of shows you where coated steel sits compared to some of the other materials that we've looked at in the past. Some of the data that's available from them. So there's your introduction to EPDs, really fast and furious. Now what do we do? Okay. And we all have this, I think we have experience, our experience with EPDs and LCAs have probably been in the context of a green building program, if it's LEED, if it's green globes, or maybe even ASHRAE 189.1. And the use of these documents in those programs is pretty well documented. I'm gonna make this pretty quick. But LEED gets into it in the MR credits. I'm talking about version 4.1. The environmental product declaration has its own credit. Those are the potential applications for them. Just come straight out of the LEED reference guide. And option 1 is specifically where EPDs come into play. Use at least 20 different permanently installed products, sourced from at least 5 different manufacturers. It meets one of the disclosure criteria below, 10 different permanently installed products from 3 different manufacturers for other types of systems. So life cycle assessment, environmental product declarations, products with a publicly available, critically reviewed life cycle assessment, which is what we've have done behind the EPDs. Complying with ISO 14044, that at least one cradle to gate scope are valued as one whole product for the purposes of the credit evaluation. And then also an EPD type 3 internally reviewed, meaning that it is internally reviewed within the process of LEED. It is a peer-reviewed document by definition as a type 3. Let's make sure that clear with that. But products with specific EPDs which conform to this ISO standard and have at least cradle to gate scope are valued as one whole product. And then you get into industry wide that are generally evaluated as one whole product. When you get into the product specific EPDs, that's when you get evaluation of 1.5. So not necessarily 20 products, I could have fewer. But again, like I said, at least in case of metal cladding, we can tell you with a pretty high degree of confidence that a product specific type 3 LPD for metal cladding is going to be that different than what you're going to get out of the industry average. This is just the option 2, where you then can take the EPD and what you've done, you've pulled these in, and now I'm going to go through an optimization process. And this is what you get for going through that optimization process and how you verify that optimization process is done. I doubt this is done too much. Certainly, I would get a lot of questions from folks doing this as I man the Ask the Expert portion of the MCA website. So at this point, we're still mostly collecting the documents and making the check the box and moving on. That's getting ready to change. But real quick, I'll just hit on a couple other programs, pretty similar type of requirements with green globes, and they're really looking still at recycled content. And recycled content is something you consider separate from the EPD because the impact or the gain, if you will, of the recycled content comes, it's built into that process. So it's all part of this average and these numbers that can run out. So you can recycle content you actually would still get from AISI or from the manufacturer directly. But they also have different documentation requirements and product specifications. So a lot of this is still kind of being done in a single attribute or multi-attribute, but non-whole building point. So again, EPDs are still mostly check the box type of documents. Just having one available is helpful, and that's great. But as manufacturers, now we need to understand what we are going to do with this data. How can we move it forward? And now we're going to talk about that. Now, we also know that LEED is moving to decarbonization over general impact reduction, as is some other groups who develop codes and standards. And so I did also want to, I put the ASHRAE 189 requirements in here under codes and standards because that's really what it is, but it's very similar to LEED in its approach. Product specific declarations, industry-wide is one product, and product specific declaration covered as two products. And I see we have some chat questions coming in here, so it might be a good way to time to break. I think all of our questions looks like they were related to getting copies of slides. Is that correct, Kaylin? That's all I see here.
Yeah, so I do actually have one other question that
Okay.
has come up. And that is that how is the recycled content of steel addressed in the LCA?
That is, let me tell you, that is a big question. So here is I'll give you a short answer and a longer answer. The short answer is it's built into the data collection, the analysis, and the modeling. It's inherent to all that. So the answer that you get includes the impact of that recycled content. Now, how exactly does that happen? This is where the answer gets pretty long, and it's really it's kind of specific to different types of products. So there's really two different ways to look at this. There's what they call the cutoff methodology and the avoided burden methodology. The cutoff methodology essentially means that I don't consider anything. I take that recycled, the gain of the recycled content of the input products at face value, and I don't really look at its reuse. So in other words, I'm taking the credit, I'm taking a likely reduced impact up front, and then I don't really look at I dispose of it as in not considering it being recycled as if it were going to landfill. And then there's the avoided burden approach, which is the second way, another way to do it, where you actually take a negative credit, so to speak, that makes up for the impact of what you gain from recycling, and you do that at the end. You get different answers depending on which approach you take. Steel is made from different processes. There are really two main processes that are used. There's basic oxygen furnace method or blast furnace method, and then EAF or electric arc furnace method, the latter of which uses much larger amounts of recycled content. They both use scrap in the feed, there's no doubt, but the EAF generally uses more. But EAF is not necessarily the ubiquitous way to make steel. And you got to remember also that when steel is made, it's being made to a certain recipe because there's certain requirements I'm trying to achieve. It's be it formability, weldability, all those things. And so the recycled content affects the chemistry in a lot of ways, particularly with carbon. And so it's not like I go to a product catalog and say, oh, here I can pick either BOF steel or EAF steel. You go to find your steel first and see if you've got a BOF option and an EOF option. You may or may not. It may not be obvious to you. If you're getting it from overseas, you probably don't know what it is. So what the industry's really had to do is just take a formalized approach towards this that's as flexible as possible with still being conservative. And so they've opted for the cutoff approach, but that is not necessarily appropriate for every steel product. And so this is actually a subject of quite a bit of debate in the industry. And one that continues on and probably will continue on for still some time. So that is a very multifaceted question. I appreciate whoever asked that.
Absolutely. We actually have another question that has come through as well. In your presentation, you've mentioned that the GWP of roll-formed cladding is 1.53 times 10 raised to the third. Is this considered a large value? In general, how can we judge if a certain GWP value is high or low without a mean of comparison?
That's a great question. So the answer is really hard because you have to do it in a proper context. And let me see, I'm gonna go back to the scope. That's probably the best place to show this. So yeah, you gotta remember this GWP is part of a cradle to gate, meaning it goes up through this A3. So I've experienced a certain carbon act up to this point. Now, I can turn, depending on the product that we're talking about, it might transport to the site more efficiently or less efficiently. It might install on the building more or less efficiently. So you can't really draw that line is what it comes down to without looking at this all the way through the use stage and the end of life. So there is no general guidance for this. And it's gonna really depend on the life of the building, what all is happening through these maintenance, repair, replacement, refurbishment cycles, operational energy use. I think insulation is not what this discussion is about, but it's probably the most obvious example. I'm going to experience some carbon release because I'm using insulation. It takes energy and resources to make it, and it's going to produce carbon. But if I put it on a building and makes it more energy efficient, I'm going to gain that back up. So it's not just the carbon. It's how efficient does that insulation apply to my particular building and my particular assembly. So you really have to go through this whole building LCA process to get that answer. And I know that's probably not what you want to hear, but that's the honest truth. It requires that analysis in that kind of depth to have an answer that's dependable, which is what makes this really difficult, because doing an LCA, a whole building LCA, is not easy. It's not quick. It requires the input from a lot of different folks, and you also really need to look at end of life as well, because that could have a lot to do with it. So if you're just going to straight out compare numbers between different materials at the end of a manufacturing scope, you're probably not going to get the answer you really are after. But that's a very good question. And what I wanted to do here real quick was go forward here to my last slide. How are we doing on time? Let me check on that real quick. Perfect. I wanted to talk about, I think we covered ASHRAE 189. I want to talk to you also about some state actions, because this is where I think this is really going to become an important subject, even more important in these two, in the area of code and standards development. We're already seeing two entities begin to look at this pretty closely. California, through their Title 24 development process this last time around, they were really not as considering of energy, straight up energy efficiency as they were decarbonization. The reason why those two aren't the same, because if I can have a very efficient way to produce energy that produces carbon, that's not necessarily good in the code's eyes under this new process. Previously, it was not really looked at, at least at a very detailed level. Might have been high level assigned. I mean, we know that burning natural gas at site probably produces a lot of carbon, but there's been not the study of the in-depth analysis that a LCA can provide done prior to this. This is really very new. And California has taken this under over the last 3 years in developing the new version of Title 24. They were the only ones, actually, that's not true. There were a lot of states, also other states, that were beginning to look at clean procurement acts. Washington, California has a clean procurement act law on the books as well. Washington, Minnesota had one, Maryland had one, several others that get into some of these carbon metrics as well. And again, they're not applied to these laws and legislation, kind of just tend to look at that bottom line answer, not taking it in the proper context. So we're very active as an industry to try to work with these entities coming up with these rules to make sure that those things are considered. And one very recently is New York NYSERDA, who is really pushing their green building and their solar efforts, are seeking input for the public concerning their draft scoping and climate action plan. So they'll be looking at this when it comes to buildings very closely as well. So we go back to the two questions that have been answered in this context, and we can see that this is an issue that's going to need resolution in our industry. We all understand that we have to get better in terms of carbon and production of carbon and global warming in general. But how to do that needs to be driven by the science, not just the math on the outside, right? And so we're working very hard as an industry now to not just within the steel industry, but with other industries as well, to really further understand what how those metrics are, how they're accounted for, meaning carbon specifically, how they compare to other materials, because we want to make sure that message is carried across, that just picking the material with the lowest carbon at the grade stage is not going to necessarily lead you to the best answer. Could very well lead you to the worst answer if it results in a poor use phase application. And nobody's touching this. Nobody wants to look at it because it's very detailed, deep discussion, and they want laws that are simple and easy to apply. And the reality is it's probably not going to happen that way. So we're going to have to push the science, push this analysis, and work with these entities to get them to further understand those aspects of it.
I do have another question that has come through, and this is coming from Andreas. I hope I pronounced that name correctly. We all are here so concerned which efforts are being made to fight China, which is using reverse engineering processes to produce all kinds of metal profiles in order to limit the span of life of every metal product we import from them.
So what I am not as aware. A lot of things that are happening overseas, primarily because we work with AISI and we really promote the use of North American steel and the use of our products. But we do, in our research and our efforts, we look a lot to Europe and to Asia as well to further understand what those potential conflicts are. It really is the biggest problem I think we have, or the biggest challenge we have, is just gaining the transparency into the processes in Asia that we have in Europe and America. And, we could talk for hours why that is, and it's probably well beyond the scope of the discussion today. But I could tell you that, in North America, certainly in Europe, and becoming a very important subject in North America as well, to further understand, the best thing that we can do is provide the users with the best transparency we can, educate the users with that, and then look to our folks overseas who aren't doing that, or aren't able to do that, or can't do that to the level at which we can, and try to convince the market to look at a broader, more applicable answer. And that's what we're really focused on. We're focused on education and outreach, and it all starts with those impacts and what we have. So I guess it's the old adage of control what you can control, and let the chips fall where they may.
Okay. Perfect. Are there any other questions coming in from our audience? Not seeing any, but figured I'd give another call. Anyone had anything?
I would, if you're interested in more about the discussions on recycled content and steel, there's actually a lot of stuff out there on 2 websites. There's American Iron and Steel Institute, which of course is despite the A in there, they're really North American focused. And they have a steel Canadian counterpart, and they work together quite a bit. So they, at least on the sustainability side, so they produce those documents for North American Steel. So you can Google those and find those. And then World Steel, which is the European counterpart to that. But the term world steel is a little misleading because they look at Europe, they look at North America, and they look at parts of Asia, but really the Chinese data, because that lack of transparency, isn't necessarily represented. So if you want to get more into that, those documents discuss the differences between closed loop. Steel is always closed loop, so there's what they call a closed loop process, which basically means that the recycled portion of what I'm producing has the same properties as the virgin material, so they can be substituted one for one. Steel is great at that. Plastic, not so much. When I recycle plastic, a plastic bottle, I can't always make it back into a plastic bottle. It might be going in some type of thread or fiber to produce a fabric that doesn't have the same use. That's an open loop. So all steel recycled contents are done with a closed loop process. It's just, how is that closed loop process implemented? Is it done upfront like the cutoff method, or is it done with a negative credit at a more of a backwards looking? And those 2 approaches do yield different answers depending on the AF and BOF steel. So a lot of information out there on that, and if you really want to get into it, those are the websites or those are the documents to look for.
Perfect. Do you have anything else that you wanted to discuss, Bob?
Well, I think we're right at time, so I'm
Perfect.
Give everybody 4 minutes of their life back.
Okay. Well, thank you everybody for joining us today. We so appreciate you being here, and a very special thank you to Bob Zabcik for joining us and presenting this fantastic discussion. We so appreciate this. Again, if you guys have any course ideas, please submit those to us. And if you have any interest in becoming an MCA member or finding out more about the MCA, you can find out more on their website. Thanks again, everybody, and have a great rest of your day. Hopefully we'll see you on February 2nd for our next MetalCon Live. Bye, everyone.
Thank you, Kaylin. Thank you, everybody.